let's talk about, let's continue talking about greatest common divisors. And ultimately, remember, the goal is for us to reach the pinnacle of the number theoretic mountain, which for us is understanding the RSA cryptographic scheme, okay? And in particular, trying to understand, the public key cryptographic scheme, which is relatively new, and number theory is at the center of it all. So I introduced you last time to this little technique that you can use to compute the greatest common divisor, if you will recall. So if I want the GCD of 35 and 8, what do? Well, we divide 35 by 8, okay? And then, so we see that that thing goes in 4 times with a remainder of 3. And at the next step, you take the divisor and the remainder and you use that in the next step. So here you see 8 and 3, okay? And at the next step, you take the divisor and the remainder and you go down to the next one, etc. And we reasoned out why it is that at each stage, we're actually preserving the greatest common divisor, because the first equation shows that anything that is a common divisor of 35 and 8, because after all, this equation is the same as 35 plus 8 times -4, or -4 is equal to 3. Anything that is a common divisor of 35 and 8 will also be a divisor of 3. Because think about it, if something divides 35 and 8, then certainly it divides that combination of 35 and 8, yes? And therefore it will divide 3, which is equal to that combination, yeah? So any common divisor of 35 and 8 is also a divisor of 3. And on the flip side, any divisor of 8 and 3, okay, so 3 is equal to 8 times 4 plus 3. Any common divisor of 8 and 3 is a divisor of 8 times 4 plus 3, and therefore is a divisor of 35, yeah? So that means that the set of common divisors for 35 and 8 is the same as the set of common divisors for 8 and 3, and therefore the greatest among those divisors would be the same, okay? So that first equation basically tells us that we can swap out 35 and 8 for 8 and 3, as far as finding greatest common divisors is concerned. And then the second line says that we can swap out the greatest common divisor of 8 and 3 for the greatest common divisor of 3 and 2. And the next line says we can swap out the greatest common divisor of 3 and 2 for the greatest common divisor of 2 and 1. This is becoming an easier and easier problem, yeah? And so this Euclidean algorithm that we use here preserves the GCD at every line. The GCD of 35 and 8 is the same as the GCD of 8 and 3, which is the same as the GCD of 3 and 2, which is the same as the GCD of 2 and 1, which is just 1. And actually, the very last non-zero remainder will actually be the greatest common divisor under this little scheme right here. Okay, so that was kind of cool. Any questions on that? By the way, this is still the algorithm that computers use to actually compute greatest common divisor. So if I go to Wolfram Alpha and I say, what is the GCD of 35 and 8? It will execute the Euclidean algorithm. It's very quick and efficient finding greatest common divisors, okay? This was kind of pseudocode. If you've seen C++, this will make more sense than if you haven't, but this is basically a computer program, or like a plan for a computer program that would deliver the greatest common divisor back to you by way of the Euclidean algorithm. And we finished last time by looking at the GCD of 662 and 414. And we kind of went through the Euclidean algorithm again, and we found out that the GCD was actually 2 by using that. And there's going to be those equations that we came up with is given in a couple of slides here, okay? But the general idea here is quite simple, as we've seen. So again, we have a very efficient way of finding the GCD of two numbers. If you write A equal to BQ plus R, where R is the remainder, and therefore the remainder is going to be between 0 and B, since B is what we divided by, then what we've shown here is that the GCD of A and B is the same as the GCD of B and R, yeah? And that's kind of the key step in us reducing our problem down to a simpler one. Okay, but the question remains, how is this going to help us find inverses? Okay, and we'll see why that happens to be the case. Remember, I said earlier, like, you know, finding inverses is pretty important. Inverses, multiplicative inverses modulo something. How is this Euclidean algorithm going to help us to that end? Well, we're going to see that here pretty soon. Okay, so watch this. This is how we find inverses. So check this out. Let's revisit 35 and 8. Okay, there's 35 and 8. There are the equations that we came up with, yeah? And what you can do is you can work backwards, okay? You can actually work backwards from the last non-zero remainder. What's the last non-zero remainder in this process? Not trying to insult your intelligence, but it's 1, yes? Okay? The last non-zero remainder is 1. And you work backwards from there. What am I doing in this first equality right here? Which equation am I using? 1. Look, 3 is equal to 2 times 1 plus 1, yeah? That's the same thing as 1 equaling 3 minus 2 times 1, yeah? All I've done is I've just subtracted this over, yeah? So I basically use this equation to say that 1 is equal to 3 minus 2 times 1, okay? And then what do? Well, I'm going to replace 2, right? Because 2 appears here, doesn't it? Yeah? I'm going to replace 2 with what it equals from the very next, like I work backwards, right? I go up to the next equation. I'm going to replace 2 with what it equals. And this equation right here says that 2 is equal to 8 minus what? 8 minus 3 times 2. So do you see that's what I did right here? Right, so 3 minus 2 times 1, okay? And then we replace 2 with 8 minus 3 times 2, and we end up with this, yeah? And that's a mess, you understand? But what I'm going to do is I'm going to preserve the 8s and the 3s, because those are the things that were important in that equation right there. So I simplify this thing. I say, how many 3s do I have? If I distribute this minus sign, how many 3s do I actually have? 3 times 3 plus 8 times minus 1. Do you see that? Yeah? And then what are we going to do? Well, I have 8, right? Remember, my goal was to get to something involving 35 and 8. I have 8, but I have this pesky 3 right here. Okay, it's 3 times 3 plus 8 times minus 1. And by the way, you can always check yourself. Remember, we started with 1. Is 1 really equal to 3 times 3 plus 8 times minus 1? Sure it is. 9 minus 8 is 1, yeah? Okay. So, but look, I have an 8 here, but I don't see 35 yet. But the next equation up, I can actually use to replace 3 by stuff that only involves 35 and 8. Because after all, this equation says that 3 is actually equal to 35 minus 8 times 4. Don't you see? Yeah? So then I'm going to actually take this 3 and put it right there, which is exactly what we do. We replace that 3 with 35 minus 8 times 4. And then I'm going to combine everything. I distribute this 3 here. And how many 35s am I going to get if I distribute that 3? 3. And it's going to be plus 8 times, okay, so look, here's a negative 1 times 8. Here's a negative 12 times 8, okay? So it's 8 times negative 1, and then an 8 times negative 12 overall, that's 8 times negative 13, yeah? So all I'm doing is I'm kind of working backwards continually solving for remainders and then plugging it into the previous equation. And I'm kind of trying to get a combination of the greatest common divisor, like an integer combination of the original numbers that give me the greatest common divisor. Okay. So in the end, we end up with 1, look at this, 1 equals 3 times 35 plus 8 times negative 13. Does that work? Let's see. 3 times 35 is 105. Yes? What's 8 times 13? 104. That comes with a minus sign. So we get 1 is equal to 35 times 3 plus 8 times negative 13. You might say, so what? How does that help? Well, I can rewrite that, correct? Isn't this the same? Do you see that? Yeah. 35 times 3 is equal to 8 times 13. What if I take this thing modulo 8? What's this part? What's going to happen to 8 times 13 if I take that modulo 8? What's the remainder of that? 0. So if I take everything modulo 8, this part will go to 0. Okay, and what will be the only thing that's left? 1. Do you see? So what that means is 35 times 3 mod 8 is equal to what? Think about it. So 35 times 3, if I take that mod 8, this junk just goes away because it's perfectly divisible by 8, and all that's left is 1. So what does that tell you about 35 and 3? They are inverses. 35 times 3 is 1 modulo 8. Yeah? So it turns out that this Euclidean algorithm and then using the thing backwards puts us in a position where we actually find an inverse. Okay? 35 and 8 are relatively prime to each other. They don't have any common factors. What's the only prime factor of 8? No, the only prime factor. 2. Does 2 divide into 35? No. So 35 and 8 are relatively prime. We said that things that are relatively prime are actually going to, like 35 will have an inverse modulo 8, okay? And guess what? We just found it, yeah? We found an inverse, namely 3, and the Euclidean algorithm actually helped us do that, okay? So by reversing the Euclidean algorithm in this way, it is always possible to write the GCD of 2 integers as an integer combination of them. Okay, this is a powerful thing. And we'll get some more practice with that here pretty quick. Okay, so this reversing of the Euclidean algorithm empowered us to actually find an inverse of 35 modulo 8. By the way, this is sort of silly, but I could also say, so like what would be an inverse? So watch this. Isn't it true that 8 times negative 13 is apparently equal to 35 times negative 3? 35 times negative 3 plus 1. Isn't that another way I could write this equation? Yeah? Don't you see? So let's see. What if I took this mod 35? I could also go mod 35. If I take everything mod 35, what's going to happen to the right-hand side? What's 35 times negative 3 mod 35? What's that going to go to? That's going to go to 0 because it's perfectly divisible by 35, yes? Okay. And what am I going to get here? I will get 8 times negative 13 mod 35 equals what? 1. So what does that tell us about the number 8 and the number negative 13 mod 35? They're inverses, eh? They are inverses of each other. And by the way, that's sort of weird because here the inverse of 8 ends up, one of the inverses is a negative number. Yeah.
How is negative 3 going to 35?
Negative 3. No, so when you take this thing mod 35, you're dividing this side by 35. Right, and so what's going to happen to 35 times -3 when you divide that by 35? What's the remainder of that? 0, that just goes away, and 1 just stays. Make sense? So the remainder of all that right-hand side is just 1, yeah? Okay. By the way, -13, can you think of -13 mod 35? Can you think of other things that that's equivalent to mod 35? Can you think of other things that that's equivalent to mod 35? Here's a hint. Just add multiples of what? Just add like 35 or subtract 35 or just add any multiple of 35, yeah? So what is that going to be? 22 mod 35, yeah? So I mean, another inverse, but it's really the same mod 35. Another inverse of 8 would be 22. So I'm telling you, 8 times 22 mod 35 is 1. Okay, and you could check that out. What is 8 times 22? 176, yeah? 176. 140 is divisible by 35, so 175 is divisible by 35, yes? So 176 is exactly 1 more than a multiple of 35, yes? So 22 is also serves as an inverse of 8, yeah? And all of this comes out of the Euclidean algorithm. Surprisingly, I mean, it's just shocking to me that Euclid had the mental dexterity to do this with very little in the way of like notation and you know, and mathematical rigor back in that day. Okay. Okay, so this is a very, very efficient, good way of finding inverses. And in general, it gives us a way of writing the GCD of two things as a combination of the original integers. Okay. Well, let's look at that more complicated example. Oh, by the way, what we're dealing with here is something called Bezo's theorem. Bezo's theorem says that there are integers x and y such that there are always integers x and y such that ax plus by equals the GCD of a and b. Okay, so for instance, we just did 35 and 8, right? 35 times something plus 8 times something is equal to the GCD of 35 and 8. What is the GCD of 35 and 8? 1. So what was it? It was 35 times 3 plus 8 times -13. Okay. So this was the x, right? This was the x and this was the y. Okay. So Bezo's theorem says that's always possible. Always. And it's because of the Euclidean algorithm, sort of reversing the Euclidean algorithm, that it's always possible. Last time we figured out what the GCD of 414 and 662 was. Do you remember what it was? It was 2. And so Bezo's theorem says there ought to be integers x and y such that 414 times x plus 662 times y is equal to 2. Okay. And actually we'll see what numbers x and y work. Okay. On the next slide. So here's what we did. Do you remember last time? We said 662 is 414 times 1 plus 248. Remember that? Okay. Then we said, okay, next line, you take the divisor and the remainder and you go down, yeah? 414 is equal to 248 times 1 plus 166. Then you take the divisor and the remainder and go down to the next line. 248 is equal to 166 times 1 plus 82. That's looking better. Take 166 and 82, go down to the next line. 166 is equal to 82 times 2 plus 2. Yeah? And if you go down the next line, the remainder is 0. And you say, okay, if I back up to the previous line, we're in better shape here. And then what am I doing right here? What am I doing? 2 equals... What am I doing to get, what if I write 2 equals to 166 minus 82 times 2? What am I doing? I'm using this guy right here, yeah? So I'm saying that 2 is equal to 166 minus 82 times 2. I'm trying to work back to the original numbers, 414 and 662. So, and then what do? I replace 82 with what it equals, okay? What's 82 equal to? Well, so it's going to be 166 minus, what's 82? Well, it's 248 minus 166 times 1. And this is multiplied by 2. After all, this is 82, okay? Kind of a funny way of writing 82, but oh well, right? Then what do? I combine stuff. And I say, well, how many 166s do I have? Right, I have one here, and then I have these two. There's a minus sign that's going to distribute, and I'm going to get 2 more 166s for a total of how many 166s? 166 times 3. And then I have how many 248s? Well, -2. And you can check that out. 3 times 166, what is that? 496 or something like that, right? Is that right, or did I totally botch that? 498, thank you. Okay, 3 times 166 is 498. 2 times 248 is 496. 498 minus 496 is 2. Right, so we're good to go so far. I always like to check to make sure things are working out. But I don't want 166 and 248. What do I really want? 662 and 414. What in the world am I going to do? Well, I'm going to use the 166 from the next line up. You see what we're doing? We're just kind of working backwards. Okay? So 166 is apparently equal to 414 minus 248. This is multiplied by 3 plus 248 times -2. Yeah? And I distribute this 3 to kind of figure out what's going on here. How many 414s do I have? 414 times 3. I distribute that 3 to the -248, -3 248s, and then -2 248s is how many 248s? 248 times -5. And you could sit here and think about that. 3 times 414, what is that? 1,242? Yeah. 1242. And 1242. What is 5 times 248? 1240. 1242 minus 1240 is 2. 2, thankfully. But I don't want 414 and 248. What do I want? I want 414 and 662. So what do? I take the 248 and I put it into this thing. Okay, so I'm going to end up with 414 times 3 plus, okay, what is 248? Well, apparently it's 662 minus 414 because of that equation. And that's going to be multiplied by -5. Yeah? And you distribute. What are we going to end up with? 2 equals, I'm going to write it over here. 2 equals what? How many 414s do we get? We have 3 right there. And then 5 more, because it's -5 414s, yes? So we get a total of 8 414s. Okay? And how many 662s do we have? Yeah, 662, oops. 662 times -5. Amazing. 8 times 414, didn't we already do that? Oh no, yeah, right. So, okay. Yeah, 3,200 plus, yeah. What is that? Okay, so say that again. 3312. And 662 times 5 is 3310. Minus, so 3312 minus 3310 is 2. So we have managed to write the GCD 414 and 662 as a integer combination of those two things, okay? And that's what Bezos' theorem says is always the case. And the reason it's true is the Euclidean algorithm, okay? It's a very powerful, powerful tool, okay? I think that's kind of neat. If you want something practical, that's pretty practical right there, okay? So you find these GCDs. This is literally an algorithm, which is just a set of rules that you follow to accomplish some task, right? I don't know if you've heard that word before, but an algorithm is a set of rules to accomplish some task. So like an algorithm for calling my mom would be pick up phone, dial number, right? Wait for phone, you know, like you would have your algorithms for doing certain things. Here we have an algorithm to find not only the GCD, but to actually write the GCD as a combination of two given integers. That's interesting, okay? A similar approach works no matter what two integers we start with. Isn't that neat? I think it is. I'm not going to let you rain on my parade, okay? So here's a couple of corollaries, remember, or as Roper would say, corollaries, okay? Look, so given three integers, A, B, and C, and suppose D is the GCD of A and B, okay? It turns out, so what does it mean for something to be a necessary and sufficient condition? It's if and only if, yeah? Okay, so suppose I stumble around and I find integers X and Y such that AX plus BY equals C. Well, what must be true about C then? Turns out the GCD has to divide that thing, has to divide C, okay? So for instance, for 414 and 662, we know that what's the GCD of 414 and 662? 2. Therefore, the only things that we're ever going to get by taking integer combinations of 414 and 662 are multiples of 2. No matter how clever you are, you take any combination of 414 and 662, you could take, 714 times 414 minus, 37,426 times 662. Whatever you get has to be a multiple of the GCD, namely 2. Like I would never be able to write 13 as a combination of those two things, okay? And again, that also I won't go into the details here, but that actually falls out of this exploration we've been doing with the Euclidean algorithm, okay? What's interesting though, like 35 and 8, for instance, so 35, what was it? It was 35 times 3 plus 8 times negative 13, that was 1, right? What's interesting is I can actually get any number as a combination of 35 and 8 now. Do you see that? Like how would I write 7 as a combination of 35 and 8? How would I write 7 as a combination of 35 and 8? Well, if I want 7, I would just multiply by 7, okay? And if I multiply by 7, the right-hand side, of course, becomes 7, yes? And I keep 35 and 8 the way they are, but I'm gonna have to multiply 3 by what? By 7, which is 21. I'm gonna have to multiply negative 13 by 7. What's negative 13 times 7? Yeah, that's negative 91. Okay, so once you have 1 as a combination of things, you know the GCD is 1, but you also know you can write any integer as a combination of those two numbers. Okay, so that's interesting. What if the GCD of two numbers was 11? Then no matter how clever I am, if I take those two numbers and I take an integer combination of those, what am I going to get? Could I ever get Could I ever get 2 as a combination? No. Could I get 11? Sure. Could I get 22? Yes. What about negative 33? Yes. Could I get 25? No, because that is not a multiple of 11. You see what I'm saying here? That's what this corollary is getting at. Okay? All right. So here's a few other little tidbits that we can take to the bank. The GCD of 2 numbers is 1 if and only if there's an integer combination of those things that gives us 1. I can go back and forth now by using the Euclidean algorithm and the Bezout theorem. Okay. If the GCD of 2 numbers is 1 and A divides a number and B divides a number, B divides that same number, okay, then look, A and B have no common things in them. Does that make sense? So if A divides a number and B divides a number, okay, so for instance, I mean, here's an example. I don't know, like 3 and 7. Like 3 divides, you know, let's see here. 3 divides, let's see, 3 divides 105 and 7 divides 105. Doesn't it? Doesn't 7 divide 105? Yeah. Therefore, what? Therefore, since the GCD of 3 and 7 is 1, look, the 3 dividing 105 has nothing to do with the 7 dividing the 105. Yes? Therefore, you can kind of combine the two of them, and the product of both is going to divide 105 also. Yeah? Since the GCD of 3 and 7 is 1, 3 times 7 divides 105 also. Okay, that's what this thing is saying right here. Okay? GCD is 1, then if the GCD of 2 numbers is 1 and they both divide something, then their product also divides that thing. Yeah? Their product will also divide that thing. If the GCD of A and B is 1 and A divides BC, then where is all the divisibility taking place? Is A dividing into B at all? Is there anything in B that's contributing to the divisibility of A into that product B times C? No. So all the divisibility has to be happening with C, yeah? Okay. So in other words, like notice 3 divides 7 times, I don't know, 21, right? But GCD of 3 and 7 is 1. So what? 3 actually, there's nothing happening with the 3 and the 7. So all the divisibility has to be happening where? 3 divides the 21, right? You can kind of just ignore the 7, okay? All of these things, these little basic number theoretic facts, are going to kind of be part of the bedrock of how cryptography happens to work. Okay, how cryptography happens to work. Yeah. Any questions on that? There's one more ingredient that we need. And it's called Fermat's little theorem, as opposed to Fermat's big theorem. Okay, which one group already talked about Fermat a little bit, yeah? Fermat's little theorem is extremely important, and it's actually going to be the very last ingredient that we need. But I actually want to show you kind of visually how this thing works. Okay, but actually, I think I'm going to hold off on the full-fledged proof. But look at these beautiful pictures we're going to be looking at. Okay, like there's going to be lots of little bracelets that we're going to make. Okay. There's going to be some cool stuff that happens with bracelets that are going to enable us to actually understand why Fermat's little theorem happens to be true. Okay, there are some very heavy, like analytical proofs of Fermat's little theorem. The one we're going to have is very visual in nature. It has to do with the number of bracelets you can form by beads of given colors, okay? So it'll be a nice, interesting proof. One of the facts is, like, do you see all those bead strings with blues and yellows? By the way, I put zeros and ones on here in case you're colorblind. I'm actually serious about that, right? So I put like zeros and ones on here just so you can tell the difference. Notice that first group of strings, they're really all the same bracelet when I put them together. You understand? Like that yellow bead is kind of shifted around, but when I put them in a bracelet, you can't distinguish them from one another. And that's going to be a key ingredient in the proof of Fermat's little theorem. But basically, Fermat's little theorem says, you give me a prime and you give me any integer, then P, the prime, will divide evenly into the difference between into the P and N. And that you might say, well, why in the world would that be important? But it turns out it's going to be the key to kind of unlocking the cryptographic scheme we're going to be looking at. It's a very important theorem for sure. Okay? All right. Here's a nice picture of Fermat to kind of stare at as we finish the lecture for today. And someone's going to talk about, that's our group on Friday is going to talk about Euler, another very famous, very important mathematician, on Friday. Okay? So we'll revisit Fermat's little theorem on Monday. That's it.